Welcome to this Blended Learning Classroom. Today we're going to learn about conversion of analog waveforms to coded pulses. I am Merlin Gilbert Raj, working as an assistant professor in the Department of Electronics and Communication Engineering here in Karunya Institute of Technology and Sciences. Yes, we're going to see about delta modulation, which actually converts the analog waveforms to a coded pulses. On the outline, we'll be looking on to delta modulation transmitter, delta modulation receiver, and the quantization error, which is the impact which is in the delta modulation. Delta modulation takes the inspiration from the differential pulse code modulation, which basically uses complexity bandwidth trade-off with reference to the standard pulse code modulation. Look at this picture, which gives you the illustration of trade-offs between the standard PCM, differential pulse code modulation, and the delta modulation. One can see that as the system complexity increases, and you can see the transmission bandwidth on the other hand decreases. So here our primary objective is to understand about the delta modulation. Why do we go for delta modulation? Since the complexity involved in DPCM is very high, we have in practice the need for reduced system complexity compared with the standard pulse code modulation. To achieve this other objective, that is to reduce the system complexity, transmission bandwidth is a trade-off for reduced system complexity, which is precisely the motivation behind the delta modulation. Yes, now in delta modulation, we have used bandwidth complexity trade-off as the heart of the technique. Here, the incoming message signal is oversampled, which requires the use of a sampling rate higher than the Nyquist rate. Therefore, one can say that correlation between adjacent samples of the message signal is purposely increased so as to permit the use of a simple quantizing strategy for constructing the encoded signal. How do you say that correlation here is higher? You can say that when you oversample a signal, when you oversample a signal, what is the meaning of that? You are taking more number of samples, right? That means the successive difference between the sample amplitude is going to be less. That is what we call it as the similarity between two successive samples is very high. That's what is termed as correlation. So purposefully here we increase the correlation between adjacent sample so that we can use a very simple strategy for quantization in order to get the encoded signal. Let's see how delta modulation transmitter reduces the system complexity to a minimum possible. We have two strategies, and having these two strategies in a combinational manner, one can say that delta modulation transmitter can achieve reduced system complexity. Let's see the first. The first is the single bit quantizer. To the right of the screen, you can see a block diagram, which is the delta modulation transmitter, which consists of a sampled or the oversampled message signal Mn, which is being fed to the comparator, and in turn the comparator has another input coming from the accumulator Z inverse. And you can also see there is a quantizer which operates with 1 bit, and then it further gives to the encoder, and further you get the delta modulation encoded signal MQ of n. So what is this strategy of single bit quantizer? The single bit quantizer uses the simplest strategy as you see in the figure, right, which actually act as a hard limiter. Hard limiter means that the output is going to be either it is going to be plus or it is going to be minus. Here in this case we use this term plus del and minus del. After quantization you will get the step size known to be del, which may be positive or negative. So based on the positive or negative value, one can encode it in a very simple way to achieve the delta modulated encoded signal M, Q, N. So the quantizer acts as a hard limiter with only two decision levels, namely plus or minus del. The second strategy what we have is single unit delay elements. So here you can see for prediction of consecutive samples, we have used or shown a simple example of a prediction filter. The example is FIR filter which has the order P. And you can see here you have n number of delay elements or n minus p number of delay elements, right? And you have p number of weight elements, which basically uses to tune the prediction in a more accurate manner. However, you can see that single unit delay element is the front end of this FIR filter. So here in single unit delay element, you can see that the message sample mn is fed to this single unit delay element. Right? This is the important function which comes with the strategy of delta modulation transmitter before or priorly before the use of the FIR prediction filter, which has the order P. And finally, you see you will get the output, which is the prediction of message sample m cap of n. So this is the holistic use of these two strategies. What are the two strategies? The two strategies are, one is single bit quantization. The single bit quantization you can see here, and we also use this single bit unit delay, single unit delay element. These two combined to give us the reduced system complexity. Mathematically, every stages of the output from different blocks can be captured in a way En equal to Mn minus M cap n. So in this picture you can see that we have E suffix n, which is the error sample, which is actually the difference between the message sample Mn and the estimated sample M cap n. But here you can denote that En also can be equal to the estimated or the predicted M cap of n minus MQ n minus 1. And the En is being fed to the input of 1-bit quantizer. So mathematically, we consider the quantizer function as signum function. In Max, we have this function called signum function, right? So what will be the input for this signum function or the quantizer? So every En sample which is fed to the single bit quantizer, right, will give us E suffix q comma n. You can see here E suffix q comma n, which is actually equal to del, which is basically the step size, and sgn is the signum function of En, which is actually the input right here. So eq of n can be written as del sgn of En, right? So that will give me either a plus del or it may give me a minus del, right, based on this value En, right? If En is greater than 0, we will get plus del. So for this case it will be En greater than 0, and for this case it is En less than 0, right? So on summarizing, we can say that on comparing these two possibilities, we can come up with a decision. The first is use of the error signal. If you use the error signal En is positive, right, we will get the approximation to be M cap n is equal to MQ comma n minus 1, which is increased by the amount del. Currently seen that the delta modulation produces a staircase approximation. You can see here based on the del size plus or minus with respect to every successive sample, you can see, right, there is a staircase approximation which comes up here, right, with the time duration equal to the sampling rate or the Nyquist rate Ts, and del being the step size. So if it is plus del, your staircase will go up. If it is minus del, the staircase will go down with respect to the message samples. So here you can see this is my message. This is my message sample, right? So moreover, the rate of data transmission in delta modulation is equal to the sampling rate Fs, which is equal to 1 by Ts, which is actually seen or shown in the figure. So as we have the staircase approximation, one can easily get the encoded delta modulated signal. So here you can see minus del, right? You give 0. Again here the staircase approximation goes below the message waveform. So it is 0. Then you can also see again it is 0. So to start with it can be 0. Then you can see you have plus del. This is the plus del quantity, you get 1. Then again this is 0 because minus del quantity. Again this one is plus del, this one is plus del, then you have another plus del, then you have another plus del, another plus del, right? So 1 2 3 4 5. So you can see consecutively 5 ones are being given as the encoded symbol. Similarly, you can see if it is minus del, it is going to be 0, plus del, it is going to be 1, and for all remaining consecutive staircase which gives us minus del is given as 0. So this is the encoded delta modulation waveform, or we say that stream of pulses. Now, this binary sequence at the modulator output can be characterized with a waveform with some 0 pulse and pulse with 1. Let's see now delta modulation receiver. It is going to be a reverse or inverse of the delta modulation transmitter. Only difference is to null out the noise or to reduce the noise, we have a low pass filter at the last part of the delta modulation receiver. So let's see about delta modulation receiver. Working through the operation of the delta modulation receiver, one can find the reconstruction of staircase approximation to the original message signal is achieved by passing the sequence of positive and negative pulses representing symbols 1 and 0 respectively through this block called accumulator. Under the assumption that the channel is distortionless, the accumulator output is the desired MQA, N, given that the decoded channel output is EQ, N. So the out of band quantization noise is high frequency staircase waveform in the accumulator output is suppressed by using a low pass filter with a cutoff frequency equal to the message bandwidth. Now let's see about quantization errors in delta modulation. There are two types of quantization error. Now practically looking at this waveform, one can say, sir, this is my original waveform, but we are getting a staircase waveform in the other way around. Like one is below the message waveform, another one is above the message waveform. So yeah, this is the quantization error or quantization distortion we are gonna talking about. The first case is what we call it as slope overload distortion. We find that the step size del is too small for the staircase approximation MQ of t to follow a steep segment of the message signal M of t, with the result that MQ of t falls behind the M of t. So you can see the staircase approximation, what you see in this place is actually well below the original message signal M of t. So the noise raised or distortion raised due to this kind of staircase approximation is what we call it as slope overload modulation. On the other hand, we have granular noise. So in contrast to slope overload mod distortion, granular noise, when the step size del is too large relative to the local slope characteristics of the message signal M of t, thereby causing the staircase approximation MQ of t to hunt around a relatively flat segment of M of t. So you can see if the staircase approximation goes above, well above the message M of t, then the information or the data introduced is what call it as granular noise. So first is slope overload noise, that is the staircase approximation is well below the message waveform, and another one is granular noise, the staircase approximation is well above the message waveform. So in this class, what are the things importantly we have to remember? First, let's say slope overload distortion, is actually due to the fact that staircase approximation, but it comes well below the message signal m of t. A larger del is needed. The step size is needed for rapid variation of m of t to reduce the slope overload distortion. In contrast to this, we have granular noise, which occurs del is too large related to the local slope characteristics of m of t. So this is very important point to highlight. The granular noise is similar to the quantization noise in the pulse code modulation. So a small del is needed for slow varying m of t to reduce the granular noise. The optimum del can only be a compromise between the two cases. So this is about delta modulation, which actually converts a analog waveform into a stream of coded pulse. Thank you.